Milankovitch theory describes the collective effects of changes in the Earth's movements upon its climate. Named after Serbian geophysicist and astronomer Milutin Milankovitch, who in the 1920s had theorized that variations in eccentricity, axial tilt, and precession of the Earth's orbit determined climatic patterns on Earth through orbital forcing. The Earth's axis completes one full cycle of precession approximately every 26,000 years. At the same time, the elliptical orbit rotates more slowly. The combined effect of the two precessions leads to a 21,000-year period between the astronomical seasons in the orbit. In addition, the angle between Earth's rotational axis and the normal to the plane of its orbit oscillates between 22.1 and 24.5 degrees on a 41,000-year cycle. It is currently 23.44 degrees and decreasing. Similar astronomical theories had been advanced in the 19th century by Joseph Adhemar, James Kroll and others. But verification was difficult due to the absence of reliably dated evidence and doubts as to exactly which periods were important. Not until the advent of deep ocean cores and a seminal paper by Hayes, Embry, and Shackleton, Variations in the Earth's Orbit, Pacemaker of the Ice Ages, in Science did the theory attain its present state. Earth's movements. As the Earth spins around its axis and orbits around the Sun, several quasi-periodic variations occur due to gravitational interactions. Although the curves have a large number of sinusoidal components, a few components are dominant. Milankovitch studied changes in the orbital eccentricity, obliquity, and precession of Earth's movements. Such changes in movement and orientation alter the amount and location of solar radiation reaching the Earth. This is known as solar forcing. Changes near the North Polar area, about 65 degrees north, are considered important due to the great amount of land. Land masses respond to temperature change more quickly than oceans, which have a higher effective heat capacity. Because of the mixing of surface and deep water and the fact that the specific heat of solids is generally lower than that of water, orbital shape. The Earth's orbit is an ellipse. The eccentricity is a measure of the departure of this ellipse from circularity. The shape of the Earth's orbit varies in time between nearly circular and mildly elliptical, with the mean eccentricity of 0.0019 as geometric or logarithmic mean. The major component of these variations occurs on a period of 413,000 years. A number of other terms vary between components 95,000 and 125,000 years, and loosely combine into a 100,000-year cycle. The present eccentricity is 0.017 and decreasing. If the Earth were the only planet orbiting our Sun, the eccentricity of its orbit would not perceptibly vary even over a period of 1,000,000 years. The Earth's eccentricity varies primarily due to interactions with the gravitational fields of Jupiter and Saturn. As the eccentricity of the orbit evolves, the semi-major axis of the orbital ellipse remains unchanged. From the perspective of the perturbation theory used in celestial mechanics to compute the evolution of the orbit, the semi-major axis is an adiabatic invariant. According to Kepler's third law, the period of the orbit is determined by the semi-major axis. It follows that the Earth's orbital period, the length of a sidereal year, also remains unchanged as the orbit evolves. Orbital shape and temperature. As the semi-minor axis is decreased with the eccentricity increase, the seasonal changes increase. But the mean solar irradiation for the planet changes only slightly for small eccentricity, due to Kepler's second law. The intensity of seasons is not solely governed by Earth's distance from Sun, season. The relative increase in solar irradiation at closest approach to the Sun compared to the irradiation at the furthest distance is slightly larger than 4 times the eccentricity. For the current orbital eccentricity, this amounts to a variation in incoming solar radiation of about 6.8%, while the current difference between perihelion and aphelion is only 3.4%. Perihelion presently occurs around January 3, while aphelion is around July 4. When the orbit is at its most elliptical, the amount of solar radiation at perihelion will be about 23% more than at aphelion. The higher eccentricity also causes extra behavior due to precession and axial tilt. The true global summer does not appear to be the warmer part of the year in the north. Seasons always arrive early, but not the same for differing seasons, since elliptical motion with respect to the Sun differs per season arrival. Orbital mechanics requires that the length of the seasons be proportional to the areas of the seasonal quadrants. So when the eccentricity is extreme, the Earth's orbital motion becomes more non-uniform and the lengths of the seasons change. When autumn and winter occur at closest approach, as is the case currently in the northern hemisphere, the Earth is moving at its maximum velocity and therefore autumn and winter are slightly shorter than spring and summer. Thus, summer in the northern hemisphere is 4.66 days longer than winter and spring is 2.9 days longer than autumn. But as the orientation of Earth's orbit changes relative to the vernal equinox due to apsidal precession, the way the length of the seasons are altered by the non-uniform motion changes, since different sections of the orbit are involved. When the Earth's apsides are aligned with the equinoxes, the length of spring and summer equals that of autumn and winter. When they are aligned with the solstices, either spring and summer or autumn and winter will be at its longest. Increasing the eccentricity lengthens the time spent near aphelion and shortens the time near perihelion. Changes to the eccentricity do not by themselves change the length of the anomalistic year or the Earth's mean motion along its orbit, since they are both functions of the semi-major axis. Axial tilt. The angle of the Earth's axial tilt varies with respect to the plane of the Earth's orbit. These slow 2.4 degrees obliquity variations are roughly periodic, taking approximately 41,000 years to shift between a tilt of 22.1 degrees and 24.5 degrees and back again. When the obliquity increases, the amplitude of the seasonal cycle in insolation increases, with summers in both hemispheres receiving more radiative flux from the Sun, and winters less. Conversely, when the obliquity decreases, summers receive less insolation and winters more. But these changes of opposite sign in summer and winter are not of the same magnitude everywhere on the Earth's surface. At high latitude, the annual mean insolation increases with increasing obliquity, while lower latitudes experience a reduction in insolation. Cooler summers are suspected of encouraging the onset of an ice age by melting less of the previous winter's precipitation. Because most of the planet's snow and ice lies at high latitude, it can be argued that lower obliquity favors ice ages for two reasons: the reduction in overall summer insolation and the additional reduction in mean insolation at high latitude. Scientists using computer models to study more extreme tilts than those that actually occur have concluded that climate extremes at high obliquity would be particularly threatening to advanced forms of life that presently exist on Earth. They noted that high obliquity would not likely sterilize a planet completely, but would make it harder for fragile, warm-blooded land-based life to thrive as it does today. Currently the Earth is tilted at 23.44 degrees from its orbital plane, roughly halfway between its extreme values. The tilt is in the decreasing phase of its cycle, and will reach its minimum value around the year 11,800 CE. The last maximum was reached in 8,700 BCE. This trend enforcing, by itself, tends to make winters warmer and summers colder, as well as cause an overall cooling trend. Axial precession. Precession is the trend in the direction of the Earth's axis of rotation relative to the fixed stars, with a period of roughly 26,000 years. This gyroscopic motion is due to the tidal forces exerted by the Sun and the Moon on the solid Earth, which has the shape of an oblate spheroid rather than a sphere. The Sun and Moon contribute roughly equally to this effect. when the axis points toward the Sun in perihelion. The northern hemisphere has a greater difference between the seasons while the southern hemisphere has milder seasons. When the axis points away from the Sun in perihelion, the southern hemisphere has a greater difference between the seasons while the northern hemisphere has milder seasons. The hemisphere that is in summer at perihelion receives much of the corresponding increase in solar radiation, but that same hemisphere in winter at aphelion has a colder winter. The other hemisphere will have a relatively warmer winter and cooler summer. When the Earth's axis is aligned such that aphelion and perihelion occur near the equinoxes, the northern and southern hemispheres will have similar contrasts in the seasons. At present, perihelion occurs during the southern hemisphere's summer, and aphelion is reached during the southern winter. Thus, the southern hemisphere seasons are somewhat more extreme than the northern hemisphere seasons, when other factors are equal. Apsidal precession. In addition, the orbital ellipse itself precesses in space, primarily as a result of interactions with Jupiter and Saturn. Smaller contributions are also made by the Sun's oblateness and by the effects of general relativity that are well known for Mercury. The total orbital precession is in the same sense to the gyroscopic motion of the axis of rotation, shortening the period of the precession of the equinoxes with respect to the perihelion from 25,771.5 to 21,636 years. Apsidal precession occurs in the plane of the ecliptic and alters the orientation of the Earth's orbit relative to the ecliptic. In combination with changes to the eccentricity, it alters the length of the seasons. Orbital inclination. The inclination of Earth's orbit drifts up and down relative to its present orbit. Milankovitch did not study this three-dimensional movement. This movement is known as precession of the ecliptic, or planetary precession. More recent researchers noted this drift and that the orbit also moves relative to the orbits of the other planets. The invariable plane, the plane that represents the angular momentum of the solar system, is approximately the orbital plane of Jupiter. The inclination of Earth's orbit drifts up and down relative to its present orbit, with a cycle having a period of about 70,000 years. The inclination of the Earth's orbit has a 100,000-year cycle relative to the invariable plane. This is very similar to the 100,000-year eccentricity period. This 100,000-year cycle closely matches the 100,000-year pattern of ice ages. It has been proposed that a disk of dust and other debris exists in the invariable plane, and this affects the Earth's climate through several possible means. The Earth presently moves through this plane around January 9 and July 9, when there is an increase in radar-detected meteors and meteor-related noctilucent clouds. A study of the chronology of Antarctic ice cores using oxygen-nitrogen ratios in air bubbles trapped in the ice, which appear to respond directly to the local insolation, concluded that the climatic response documented in the ice cores was driven by northern hemisphere insolation as proposed by the Milankovitch hypothesis. This is an additional validation of the Milankovitch hypothesis by a relatively novel method, and is inconsistent with the inclination theory of the 100,000-year cycle. Problems. Because the observed periodicities of climate fit so well with the orbital periods, the orbital theory has overwhelming support. Nonetheless, there are several difficulties in reconciling theory with observations. 100,000-year problem. The 100,000-year problem is that the eccentricity variations have a significantly smaller impact on solar forcing than precession or obliquity, according to theory, and hence might be expected to produce the weakest effects. However, the greatest observed response in regard to the ice ages is at the 100,000-year timescale. even though the theoretical forcing is smaller at this scale. During the last 1 million years, the strongest climate signal is the 100,000-year cycle. In addition, despite the relatively great 100,000-year cycle, some have argued that the length of the climate record is insufficient to establish a statistically significant relationship between climate and eccentricity variations. Various explanations for this discrepancy have been proposed, including frequency modulation or various feedbacks. Some models can reproduce the 100,000-year cycles as a result of nonlinear interactions between small changes in the Earth's orbit and internal oscillations of the climate system. Stage 5 problem. The Stage 5 problem refers to the timing of the penultimate interglacial that appears to have begun 10,000 years in advance of the solar forcing hypothesized to have caused it. Effect exceeds cause. The effects of these variations are primarily believed to be due to variations in the intensity of solar radiation upon various parts of the globe. Observations show climate behavior is much more intense than the calculated variations. Various internal characteristics of climate systems are believed to be sensitive to the insolation changes, causing amplification and damping responses. The unsplit peak problem. The unsplit peak problem refers to the fact that eccentricity has cleanly resolved variations at both the 95 and 125 Ca periods. A sufficiently long, well-dated record of climate change should be able to resolve both frequencies. However, some researchers interpret climate records of the last million years as showing only a single spectral peak at 100 Ca periodicity. The transition problem. The transition problem refers to the switch in the frequency of climate variations 1 million years ago. From 1 to 3 million years, climate had a dominant mode matching the 41 Ca cycle in obliquity. After 1 million years ago, this switched to a 100 Ca variation matching eccentricity, for which no reason has been established. Identifying dominant factor. Milankovitch believed that decreased summer insolation in northern high latitudes was the dominant factor leading to glaciation, which led him to deduce an approximate 41 Ca period for ice ages. Subsequent research has shown that ice age cycles of the Quaternary glaciation over the last million years have been at a 100,000-year period, leading to identification of the 100 Ca eccentricity cycle as more important, although the exact mechanism remains obscure. Present and future conditions. As mentioned above, at present, perihelion occurs during the southern hemisphere's summer and aphelion during the southern winter. Thus, the southern hemisphere seasons should tend to be somewhat more extreme than the northern hemisphere seasons. The relatively low eccentricity of the present orbit results in a 6.8% difference in the amount of solar radiation during summer in the two hemispheres. Since orbital variations are predictable, if one has a model that relates orbital variations to climate, it is possible to run such a model forward to predict future climate. Two caveats are necessary: that anthropogenic effects may modify or even overwhelm orbital effects, and that the mechanism by which orbital forcing influences climate is not well understood. In the most prominent anthropogenic example, orbital forcing from the Milankovitch cycles has been in a cooling phase for millennia. But that cooling trend was reversed in the 20th and 21st centuries due to warming caused by increased anthropogenic greenhouse gas emissions. The amount of solar radiation in the northern hemisphere at 65 degrees north seems to be related to occurrence of an ice age. Astronomical calculations show that 65 degrees north summer insolation should increase gradually over the next 25,000 years. A regime of eccentricity lower than the current value will last for about the next 100,000 years. Changes in northern hemisphere summer insolation will be dominated by changes in obliquity epsilon. No declines in 65 degrees north summer insolation, sufficient to cause a glacial period, are expected in the next 50,000 years. An often cited 1980 study by Embry and Embry determined that, ignoring anthropogenic and other possible sources of variation acting at frequencies higher than 1 cycle per 19,000 years, this model predicts that the long-term cooling trend that began some 6,000 years ago will continue for the next 23,000 years. More recent work by Berger and Loutre suggests that the current warm climate may last another 50,000 years. Other planets in the Solar System. Other planets in the Solar System have been discovered to have Milankovitch cycles. Mostly these cycles are not as intense or complex as the Earth's cycles, but do have a global geological impact with respect to the movement of mobile solids like water or nitrogen ices or hydrocarbon lakes. Mars's polar caps vary in extent due to orbital instability related to a latent Milankovitch cycle. Saturn's moon Titan has a 60,000-year cycle that changes the location of the methane lakes. Neptune's moon Triton has a similar variation to Titan with respect to migration of solid nitrogen deposits over long time scales.